Electrons, the tiny particles that carry electricity through every wire in your house, move at 0.2 millimeters per second. That's slower than a garden snail. But flip a light switch, and the light turns on instantly. How? How does electricity travel hundreds of kilometers in a fraction of a second if the particles carrying it barely move? In the next 8 minutes, you'll understand how electricity actually works, from power plant to your phone charger. And at the end, I'll solve the Snail Paradox. Let's start small, really small. Everything around you is made of atoms, and atoms have electrons orbiting their nucleus. Most electrons are locked in place, but the outermost ones, called valence electrons, can break free, and when they do, they jump to the next atom, and the next, and the next. That chain of electrons moving through a material, that's the simplest useful picture of electricity, just electrons being pushed from atom to atom. But not every material lets electrons flow. Metals like copper have loose outer electrons. We call them conductors. Plastic, rubber, glass, their electrons are locked tight. Those are insulators. That's why your charging cable has copper inside and plastic outside. So copper lets electrons flow. But remember, those electrons are absurdly slow. We'll get to that. So electrons can move, but what makes them move? Think of a battery as an electron pump. One side is packed with electrons, the other side is nearly empty. That difference in electron pressure, that's what pushes them through the wire. Connect a wire between both sides, and electrons flow from high pressure to low pressure, a closed loop. That's a circuit. Break the loop, the flow stops, the light goes out. Now, you might have seen this image before, and it's actually a perfect explanation. Voltage is the push, how hard the electrons are being shoved. Current is the flow, how many electrons pass a point per second. And resistance is the friction, how much the material fights back. More push, more flow. More friction, less flow. That's Ohm's law in one sentence. Try this. Rub your hands together, slowly at first, then faster. The harder you push, the hotter they get. That's friction turning motion into heat. Electrical resistance does something very similar. Electrons bump into atoms, the atoms vibrate, and vibration is heat. And sometimes, resistance is the whole point. An electric space heater is just a long wire with high resistance. Current flows through, the wire heats up, and that's your warmth. Same physics, on purpose. Remember that, it comes back later. So far, we've talked about electrons flowing in one direction. That's called direct current, DC. It's what batteries produce, and it's simple. But the electricity in your wall outlet is different. Those electrons don't flow in one direction. They vibrate back and forth, 50 to 60 times per second. That's alternating current, AC. Why AC? One word, transformers. AC can be easily transformed. Crank the voltage up for long-distance transmission, then bring it back down for your home. That single advantage decided a massive fight in the 1880s between Edison and Tesla, and changed the world. And funny enough, the device in your pocket? It runs on DC. Your charger converts AC back to DC. Edison would have loved that. But here's something weird. In an AC wire, the electrons don't even go anywhere. They just vibrate back and forth in place. So what actually carries the energy? Almost there. Here's the full picture. Most large-scale power generation comes down to one trick: spin a turbine. That turbine spins magnets near coils of copper wire, and that motion pushes electrons. Magnets and copper, that's the core of almost every power plant. The electricity gets transformed up to 400,000 volts, because higher voltage means lower current, and lower current means less energy lost as heat in the cables. Once it reaches your neighborhood, a transformer steps it back down. 230 volts in Europe, 110 in the US. And here's something interesting. Coal, gas, nuclear, they all do the same thing. Boil water, make steam, spin a turbine. That's a lot of steps, and every step wastes energy. Wind and hydro skip the boiling and spin the turbine directly. And solar? Solar skips everything. A photon hits a panel and knocks an electron loose. No turbine, no generator, and it produces pure DC. Edison would have loved that too. But the end product? Always the same, electrons being pushed through wires. So now, let's answer the big question. Remember our snail? Electrons drift at 0.2 millimeters per second. At that speed, it would take an electron over 80 minutes just to travel 1 meter of wire. 1 meter. Let's put that in perspective. Here's a race. Electrons versus snails. At 1 amp, the electron crawls at 0.07 millimeters per second. Crank it up to 10 amps, still only 0.7. A garden snail does 1 millimeter per second, and the giant African snail? 3 millimeters per second. It's not even close. Every snail wins, every time. So let's settle this with a race. The snail gets the Ferrari, the electron gets the Beetle. And it's still not a fair race. The snail wins every single time. So if the thing carrying your electricity is this slow, what do you think actually makes the light turn on instantly? The electrons? Or something else? Picture a garden hose that's already full of water. You turn the tap, and water comes out the other end immediately. Not because the water traveled from one end to the other, but because the push traveled through the water that was already there. Electricity works the same way. The wire is already full of electrons. The electric field, created by the power plant, is already there, pushing against every electron in the wire. But the circuit has a gap. The light switch is open. Nothing flows. The moment you flip the switch, you close that gap. You complete the loop. And instantly, a change ripples through the electric field at about 90% the speed of light, roughly 270,000 kilometers per second. Every electron in the wire starts moving at the same time. So when you flip a light switch, you're not sending anything. You're closing a gap. The electrons were already there. The field was already there. All the switch does is complete the circuit, and the field does the rest. Think about it. A human blink takes about 300 milliseconds. In that time, the electric field has traveled 80,000 kilometers. That's twice around the Earth. Before you can blink. The power plant didn't send you electrons, it sent you a push. And remember our friction experiment? The electrons barely move, but they do push against resistance. And that friction creates heat. That's why your phone charger gets warm. It's not a defect, it's physics. It's called Joule heating, and it happens in every single wire, everywhere. From power plant to your phone charger, electricity is just electrons being pushed around, slowly. But the push travels at nearly the speed of light. Oh, and remember when you rubbed your hands together? That's friction creating heat. Same idea as resistance in a wire. But here's the thing. Friction between your hands also involves electrons, and the actual mechanism goes way deeper than you'd think. If you want that video, tell me in the comments. If this changed how you think about electricity, hit like. It tells YouTube this video is worth showing to other people. Subscribe to The Curious Signal, and I'll see you in the next one.